Okay, I'm going to talk very quickly and superficially about seismology as it relates to the issue at hand, which is trying to get constraints for temperature structure, either radially, laterally, and throughout the Earth. And begin by saying that seismology provides valuable information, but it does not provide temperatures per se. Seismology, great tool for probing in the Earth, P waves and S waves going through the Earth, free oscillations. We've heard a lot in the CIDR program about that for the last couple of weeks. Waves going through the Earth can be recorded at the Earth's surface, transmitting with properties that primarily vary with depth and allow us to accumulate large numbers of paths through the Earth where we can measure the travel times, identify the primary radial structure of the planet, the layering. This is going to feed into the temperature structure, of course, as Lars indicated. But we can characterize this and fit with a 1D Earth model quite well the primary features of the multiple phases traveling through the Earth, P waves and S waves, and their interactions with the free surface, multiple bounces off of it, their interactions with the core, and more subtly interactions with small-scale discontinuities in the interior. And that has been practiced since about the 1940s. We had good enough Earth models to predict the P wave travel time to distances about 60 to 80 degrees away in the Earth that were accurate to within a couple of seconds. Okay, so very decent models available in the 40s, but it's not until the 1960s that we begin to get information about the upper mantle discontinuities, which play a critical role in temperature structure. And by 1981, that was kind of codified in this frequently cited PREM Earth model, 1D radial Earth model, which has discontinuities, something weird at 220. Ignore that, it's all imaginary. Was Don Anderson saying, oh, there's got to be something there. And then the 400 and 670, more commonly identified now as 410 and 660 as better average depths than in PREM. And P, S, and density being inferred by primarily P wave and S waves to get the velocities, mode constraints to get the density structure. And that would go all the way down to the center of the Earth with the shear velocity outer core vanishing. Now, beware of models. This model involves a lot of data, a lot of mixing of data to give an average Earth structure. And to do that and to get a very detailed gradient of density in these models, that's not provided by the data at all. It's provided by assumptions. Starting models that were used in PREM that were perturbed from assumed Adams-Williamson equation. They assumed isentropic compressibility. So to come back after the fact, you get a model and say, wow, it looks like it's on an isentropic. Well, it means that it did not deviate significantly from the assumptions. There was no information to cause it to deviate. So you get back what you put in when there's no information to change it. So if you find the Bullen parameter is 0.99 in the core, or 1, that just means it's 1 because they had no information to cause a significant deviation from the starting assumptions. Every model has some sort of embedded processing assumption. That one actually embeds a thermal assumption into the construction of this model. And to turn around and try and infer a thermal constraint from the model is circular. Circular. I'm being polite. So we want to get to this point. And it's obviously temperature is really temperature is much more important, I'm biting my tongue, than shear velocity or P velocity. It's really an important parameter in the Earth. It's an intrinsic parameter that we really want to know. But we have to be careful how we utilize seismic data to get at temperature structure, right? And we'd like to have some idea. I don't like the idea that there's a reference geotherm anywhere. It's been described. It should be a distribution of such. We can put bounds on that from the constraints from seismology, but we have to be careful about what assumptions are propagated from the seismology back into the inference of thermal structures. And you all are smart, so you can all do that right. Okay, but let's start with a basic fact. You can do seismology. You can come up with Earth models for p velocity and s velocities early in the 1940s, which know absolutely nothing, make no assumptions whatsoever about temperature structure. Okay, so you can get Earth models from seismology with no information injected from temperature structure. There's a subtle injection of such information in the construction of PEM and PREM, because Adam was a really smart guy, and he knew you have to stabilize the inversion to give a finely resolved parameterization of the Earth, rather than what the 4 or 5 layers of density that you might have been able to resolve intrinsically. So early models could do it without any assumption, and that tells you that the Earth models from seismology basically don't tell you anything about velocity directly, because you can get those models without having, they don't tell you anything about temperature directly, I'm sorry, because you can get those models without assuming anything about temperature. Okay? So to hope that you can suddenly invert for temperature from them is optimistic. What you have to have is additional information to utilize the valuable information from seismology. I'm not saying it's not valuable for constraining temperature, but it's going to be very dependent on the stuff you heard before, which is mineral physics, bulk chemistry, the phase equilibria, the effects of volatiles and fluids. All those have to be accurately sorted out to map back from seismology models to temperature structure. So my talk is far less important than Lars's. That's usually true. But okay. Nonetheless, seismology does provide some valuable guidance to how you might frame your thermal models for the Earth, either the best average 1D temperature model, which I think is a meaningless model, just as meaningless as PREM in terms of saying any specific place in the Earth must adhere to it, some sort of bulk composite, okay. The key tie points are the ones that have been mentioned, the 410, the 660, and the inner core boundary. Okay? And we can make that because seismology can reveal those depths, which gives you the pressure at which something happens in the Earth to change the seismic velocities. We can do that pretty well with probably 10-kilometer uncertainty on average in any one spot, and we can actually map out some lateral variations in these. But we can get those depths. Okay? So that's a critical input. If you then have an interpretation for what is causing that seismic velocity change, olivine to wadsleyite, or wadsleyite to ringwoodite, or ringwoodite going to perovskite, you can make a connection to temperature if you know the composition well enough and can experimentally determine what the temperatures are at that corresponding pressure indicated by the depth from the seismic models. Then you can make an inference of temperature. But of course, it depends on what you assume, whether there's an effect of having polymineralic material. Does that have an effect on where the phase boundary is? Maybe not. Does it matter whether you have hydrous material present? That probably can move phase boundaries up and down in PT, which means that T moves for this particular P that we know the discontinuity exists at. But that's all compositional and mineral physics. The seismology just gives you a pressure, okay? That something happens at that pressure. We can infer that pretty well. And that will hold for the inner core, even though it's a change in state. And of course, then the big uncertainty is going to be the alloy component and the degree to which it partitions into the core or into the outer core. The one other possibility that's emerged in the last 20 years or so is the D double prime discontinuity. It may be another tie point, and it would be very valuable because there's a big difference in depth between these guys, okay, where you could actually say somewhere in the Earth what the temperature is. That's 3 places as far as I can tell. We might have one in between if the D double prime discontinuity can reliably be associated with the phase transition, Bridgmanite to post-Bridgmanite or post-perovskite. If you can really determine that that's in fact the correct explanation, you got the pressure temperature of that phase transition, we would have a really valuable intermediate 2,700 kilometer deep absolute temperature measurement. Okay? So that would be very valuable. So those are the first order absolute temperature tie points from seismology. And of course they are associated with, these are early models from Steve Graham from Upper Mound. They're still great models, showing structure at 400, 660 for P waves and S waves. There's a lot of complexity in the upper mantle that shows regional variations, the western U.S., eastern U.S., young, old ocean. There's a lot of variation in the lithosphere and in the asthenosphere. But these guys are relatively stable. It doesn't appear to be kind of dominated by compositional heterogeneity at these depths. So you have a good chance that you could say they are a particular mineralogy affecting these transitions and calibrate their PT laboratory determinations to get the temperatures at the pressures indicated here. Okay, but what you're getting from seismology is the strength of the discontinuity, but most critically, the depth of it. The strength is going to matter, or it's going to be influenced by how much other stuff is there that is not transforming at that depth. We could do that for these two discontinuities. So the 400, 410, 660 are the critical ones. They've been around a long time. They've been exploited a lot to get temperature estimates. And my understanding from talking with Quentin is that the experimental constraints on the temperature here is still better than here. Okay? And they both are well understood. Now, Dan Shim can make this nice color plots of what happens going from olivine to wadsleyite to ringwoodite and going on to perovskite and the dissociative transition that gives you ferropericlase. So we know these are good candidates for what's happening to one part, perhaps 60% of the upper mantle being associated with these specific boundaries. Now, seismology can also reveal that these boundaries have some undulations on them, and because they do have experimentally determined clapeyron slopes, and these slopes are different for the 410 and for the 660, we could anticipate that there would be variations in the depth of these associated with temperature variations. So while not giving you an absolute temperature tie, you might get lateral variations in temperature from undulations of the 410 or the 660. Okay, but you have to determine the clapeyron slopes. Well, you have to know that these structures are in fact of the bulk chemistry for the temperature regime they're in. And that temperature regime may be different within a slab than outside of a slab. And this could shift what the bulk composition state is as well, because the slab has been chemically differentiated. So you have to know a lot, but it's not really seismological input. When the seismology might tell us these little depth variations, those are pressure variations, so you can map into the temperature variations that would be associated with them. You can do it on a global basis. People have used underside reflections, like illustrated here, SS precursors. Peter Shearer did a great contribution in mapping these out the first time globally. A lot of subsequent work with these phases, also with S to P conversions and receiver function treatments are mapping out small-scale, large-scale variations in these discontinuities. And it's all giving you temperature fluctuations around the 410, but the absolute value at which the temperature at that boundary is going to be kind of a mean value calibrated for the particular phase change. And that assumes that we know those phase changes are correct, and they're probably okay. There seems to be a lot of olivine in here. When you get down below the 670, 660, not a lot happens in the PES and density structure down to the base of the mantle. So on average, you're pretty safe of saying that there's not a major compositional stratification, but there's indications something may be happening at 1100 or 1150, thereabouts in the Earth. It doesn't show up in average Earth models as a strong transition. But if it involves a compositional change, if you have more silica in the deep mantle, you could have some stratification. You could have a thermal boundary embedded in this. And that's going to change your temperature extrapolation from your tie point of the absolute temperature here all the way down to the inner core over here, which your other tie point is. But D double prime does stand out as a bit anomalous. And there were a lot of studies in the 70s, in the 80s. That's of last century. It's really old stuff. I participated in some of that. And it was recognized that as you go toward the core mantle boundary, there are perturbations in the S velocity structure and the P velocity structure. And here's the core mantle boundary. And in particular, as you approach the core mantle boundary, the velocity gradients tend to reduce. Okay, well, if you could get detailed deviation from a smoothly increasing velocity variation, you might be able to interpret that as a thermal boundary layer effect, which would be a super adiabatic temperature gradient, causing velocities to reduce with depth, or the rate of increase to reduce with depth, and not all of them go negative. Prem itself will kind of flatten out. But many of the models have negative gradients. In particular, models determined from diffracted S waves showed negative velocity gradients that support the idea that there's a thermal boundary layer. And you could get a constraint on the boundary layer thickness. We saw that that might have been important in an earlier talk. If you can get the boundary layer thickness and get the temperature contrast across that from dynamical modeling, you might be able to get some handle on the temperature structure. It is, however, very difficult to get the gradient of the velocity structure in this region because the region is generally very heterogeneous. There's a lot of trade-off between lateral heterogeneity and radial gradients in all the models here. These are kind of local 1D models, but there's some sort of realization of a 1D average of a 3D structure, and they may be biased. The other aspect that's more promising, perhaps, is that there could be a velocity increase in various places. I spent my youth pursuing that possibility, identifying that there was indeed a reflection at some places around the world of a phase coming from the top of this D double prime region. You can see it right here. It's called SCD. S is a wave turning in the middle of the mantle. SCS is reflecting off of it. SCD was a phase going down and interacting, being refracted by a velocity increase as we modeled it. And then you can see that phase there, and you say, well, that's not much to write a thesis about, but they let me get by with it. You come up with velocity models to match that timing and amplitude, very similar to what would have been done for getting the 410 and 660. You get the depth, you get the velocity contrast pretty well. And we see again that the depth varies somewhat in place to place. These are different regions with different models, but they all have a first order kind of feature there, suggested a rapid velocity increase. And then when we're honest, we say, well, it could actually be distributed over 30 to 50 kilometers in depth, so that's a pressure range. And it could be an important phase loop in your phase equilibria for a perovskite to post-perovskite transition, if that's what it is. Well, basically a couple hundred kilometers thick, as much as 3% shear velocity increase, P velocity ambiguous, sometimes strong, several percent, sometimes missing, sometimes negative. And this then was speculated as possibly a phase change. Seismologists just guessed that maybe a phase change, but then in 2004, I first heard about the possibility here at CIDR, 2004, that there was actually discovery of a phase change in perovskite that might have the right attribute, particularly strong increase in shear velocity, modest effect on P velocity, and a change in anisotropy. That was perovskite post-perovskite, or Bridgmanite to post-Bridgmanite. Yeah, you can't call it post-Bridgmanite, right? It's not been observed. So it's got to be Bridgmanite to post-perovskite. Mineral physicists are really complicated. It does make some predictions if that's correct. One is that the D double prime layer below the discontinuity should be anisotropic. And I think it's cool that there may actually be some data to support that. These are data where the first arrival is S turning above D double prime, and these are two components, SV and SH. You can see they're lined up, this peak and that peak, they kind of line up. The middle peak is the reflection off the top of the discontinuity, which doesn't penetrate much at all into the layer. And those are lined up on SH and SV. So I got a peak, two peaks. And back here is SCS. Now SCS on this component should be down, on this component up. But you can see they're not at the same time. The SH component comes in earlier than the SV. And this would be consistent with the idea that the D double prime material under the discontinuity is anisotropic, with SH being faster than SV for this path. Yeah?
What is the distance for this feature?
This are about 80 degrees, or 78 to 80 degrees, I don't remember. It's wide angle triplication range. Okay, so anyway, there's seismological input to the mineral physics interpretation of the structure that gives you some confidence, and then you have to go and get the thermal structure. We can also map out these discontinuities in greater detail. I won't explain much. This is the core reflection. These are the phases above it. This little peak here is reflection off of this structure a couple hundred kilometers up in the mantle. Now, we find laterally varying models are necessary. They could be undulating kind of distortions, very much like the 400 and 660 undulations, but locally inferred, and you have to have a lot of data to infer this, and we can't sample globally as we can do with the upper mantle discontinuities. Can only hit this with pretty much wide-angle reflection work. So if you got Ed Garnero on your team, you kind of come up with nice graphics of models that might show explanations for these undulations. They could be due to complicated folding and contortion of cold material where the post-perovskite might be expected to occur versus some more complicated chemical stratification. Okay? But you have to have complexity there. And then there have been these spot samples. In blue, these are areas where the D double prime discontinuity was observed. Its primary importance to me is if it is really post-perovskite, and if that is calibrated in the laboratory and isn't so broad of a transition that it doesn't give this reflection, it gives you an absolute temperature tie point if you know the phase boundary characteristics and you know the composition. Unfortunately, the composition does influence the pressure and temperatures at which this would occur. Okay. Some places, like the middle of the LLSVP, should be hot if it's a big chemical pile, it's got conductive boundary layers, it's heated up. And you might not expect to see a discontinuity there, and yet we do in places that are, this is the anti-correlation, this is the bulk sound velocity, which is fast in this region, so it's blueite, whereas the S would be redite, and it looks as though there's actually discontinuities here in both P and S. Okay, so this structure could exist in LLSVPs, though that's only been sampled in a few places, mainly on paths from Tonga to North America. And we see, it's details here, but this little bump in between S and SCS is thought to be the SCD arrival. And it tends to be weaker than in the cold areas, but maybe there, and we can get the depth and velocity contrast. And in this region, more so than even in the Circum-Pacific, we see evidence that if you have a velocity increase a couple hundred kilometers above the core mantle boundary, and it varies in depth, it's this here and this here, that there is a decrease at greater depth that is about the same size. So you have a jump up, well, a little jump there. This one jumps up, jumps down. And this is the double crossing possibility. You have velocity increases paired with velocity decreases, so you'd be going through a situation where you have a jump up and a jump down by this double intersection of the local gradient in the thermal boundary layer, because this is within the deepest part of the mantle, producing two intersections with the phase boundary. Two intersections is cool because it gives you two absolute temperature points, and you've got a distance between them so you can get a thermal gradient and two tie points. Do I really believe it? It's hard because there's variability, and really there's three-dimensional structure, and probably the majority of you don't believe in post-perovskite even existing in the LLSVP because it's too hot. So maybe this is all subject to interpretation. It certainly is that. But if you go through thermal modeling, working with John Hernlin, we modeled thermal structure and tried to map out where you would have these double intersections with post-perovskite phase boundaries. You can at least come up with a self-consistent interpretation that there is laterally varying structure. You can go and estimate heat flow. But in order to be able to get this double intersection occurring in the LLSVP, you have to invoke, assuming it is hotter, you have to invoke a compositional difference relative to the surrounding mantle in order to get it to occur at the depths that it occurs. Because it's pretty much at the same depth as the transition is in cold regions. So in hot regions, you have to add iron or some other chemistry to make it occur at the same depth. But it would be a valuable temperature constraint. Okay. The last points I'll make then are with respect to the 3D structure. The structure is, I've sampled in D double prime, the very fast regions, the very slow regions indicate that there are large-scale variations, and we know this from global tomography. Okay? It's been mapped out that there are these LLSVP type structures. There are areas that seem to be supported by strong downwellings, and that this is an indicator of temperature. But to turn the tomography into temperature, you need to know thermal expansion, you need to know the composition involved, and that's all interpretive work. It's beyond, seismologists can give you color picture, mineral physicists and dynamicists have to come in to do the interpretive work. Okay, so this is intrinsically a very interactive type of area to get at temperature. But whenever we're doing that, we have to always go back and say, well, what is the seismology assumptions and constraints that I'm drawing any inferences from? And make sure you understand how they've been smoothed, how they've been regularized, what assumptions have gone into formulating the seismic model, so you don't get into that circular loop that you get in of saying, well, gee, Prem looks pretty adiabatic. Well, should be. Adam wouldn't have screwed that one up. He got that one really right. Okay, so if seismic tomography is really mapping out lateral temperature variations, and those temperature variations are modulating the occurrence of post-perovskite, you could come up with a map like this, well, I'll blame Helmberger, that is just a one-to-one mapping of seismic velocity models into the occurrence of post-perovskite, assuming that the seismic velocities indicate the depth and strength at which you would have this is elevation of where the discontinuity should be. It should be lower in the Pacific. We've seen that it's not necessarily so. And it would be higher in circum-Pacific colder regions. So you can do a lot toward temperature if you really believe your compositional interpretation. But as we've heard, we don't really know that post-perovskite even exists in the Earth. So how much do you want to hinge the estimate that it's 2,500 degrees absolute temperature, 250 kilometers above the core mantle boundary, and we know that? I'd say we don't know that with the confidence that we can make the same statement about what the temperature is at 410, 660, or the inner core. We'll hear about the inner core later. I think there has some discussion. I just want to say it's probably more reasonable to have a well-mixed, possibly adiabatic convection, but have we ever seen an adiabatic convection model? They're all produce subadiabatic gradients, but that's an assumption you could make for the core. But this is going to be the critical tie point, right? And getting the absolute temperatures, whether it's 6,000 degrees or 5,500 or 6,500, is going to depend a lot on what you assume for the composition here. And so we know that that's still an outstanding question. So any inference of the temperature structure in the core, which will be discussed later, is very uncertain for the same reasons that all the temperatures are uncertain in the mantle, whether it's truly adiabatic, what is the right composition, and nailing down that transition in state at the inner core boundary. Thank you. I'm done. Go back to checking email here. Are there any questions? Quentin.
Because it's come up multiple times over the last couple of weeks. What are the prospects of at least having the seismology community generate at least a very, very low degree model of Bullen's parameter that doesn't start with the assumption that the mantle is adiabatic? Because to me that's a very fundamental issue in the sense that if you can at least identify a zone that is not convective or shows hints of being strongly conductive, then we're at least in a place where we can start looking at at having a better constraint on where the boundary layers are and what their magnitude is.
Well, you'll violate that parameter in a super adiabatic gradient, and the boundary layers have got to be that way. Right?
Mm-hmm. Yeah, sure.
So we know D double prime will be that way by any kind of reasonable treatment of the seismology, and it looks that way. Mm-hmm. So these the plots that I think Barbara showed earlier of RMS heterogeneity versus depth kind of highlight areas that you're going to infer are significantly deviating from any reasonable kind of isochemical self-compressing domain that would have a constant Bullen parameter.
But in the context, since you alluded to it, of something happening, for example, at 1,000, for example.
Yeah.
Could you actually do a gross inversion? Just a really, and of course the problem in the Bullen's parameter is the d-rho dr term in it. Can you actually get at that from a combination of normal load and body weight and say, we didn't start with adiabaticity, we're just trying to get at, what Bullen's parameter is?
I guess let's discuss that with Jeroen. He'll probably answer that question for you because he can.
That's a dirty look from
Or maybe
Jeroen.
Barbara. But can you answer that question, Barbara? Do you feel like we can get?
I can't answer it, but I think I'm listening because we are building a reference 3D Earth model and we can
that in mind. But remember, I mean, from Miyake's talk, when you don't include some larger constraints, you get very wiggly kind of.
I didn't say it was going to be easy.
No, but I mean, I'm hearing your requests. That's all I can say.
Yeah.
So is D double prime discontinuity global discontinuity like 660 or regional discontinuity?
That's a good question. If it's global, it's variable enough in its strength that some places it's totally missed. Now, it's easy to say it's in one piece of the LLSVP, and I don't know anything outside that. And that's the truth. Could we kind of turn our spot sampling into some statistical estimation of its global extent? Probably not. You know, it's very difficult because it's very easy for it not to be observed. You have to have data at the right distance. There were a lot of negative statements that, well, you can't see it here, it's not here, but then you look at the resolution of that data and it's not sensitive enough. So you'd have to very carefully scrutinize all the specific data sets, come up with a sense. My own impression is that it's intermittent. But that's just because sometimes I think we have really clean data and I'm not seeing much. It's either fundamentally different in the relative strengths of VP and VS or something in that region so that I'm being misled, or it's not there.
Just to comment on that thickness issue, because my group has been responsible for some of those results that raise the question about post-perovskite equals D double prime assignments, is that it's not so much about whether D double prime is post-perovskite or not. I think our question, the very nature, is whether it's driven by composition or temperature. Because the thickness can be compromised for seismic detection for certain composition. As Lars showed, for example, Hatzfogite or salt can have sharp transition. So the question from myself is more about whether D double prime discontinuity is regional or local or global, makes huge implication for physics interpretation of the origin. I mean, that's not my personal view, nothing to do with community view.
I have a question. I've been wondering, is there any chance that the anisotropy in D double prime would affect our ability of detecting the discontinuity?
Oh, yeah, very much.
Has anybody checked it?
Well, people have argued that if you can actually change the path and hit with different directions, you see different manifestations, particularly in P. Mm-hmm. So the weakness of the P discontinuity has been attributed to sampling a direction where the P discontinuity is weak, and if you hit the same area with the orthogonal direction, you see a big P. Tina Thomas and others have proposed that. And it's quite plausible that anisotropy is causing some of the intermittency. The problem is typically the path coverage is one direction. And so it becomes a degenerate problem. You could probably always rotate around the anisotropy to account for non-observation, but then you're really believing that it's got to be there. Yeah. In the areas where they've been able to sample multiple azimuths, they have seen different manifestations of anisotropy. And you would expect it, right? We proposed it as SH faster than SV, and that would be a radial anisotropy, but it in detailed work looks like it's always tilted at least. And so some tilting gives you, the opportunity to get some direction variation. If it's purely radial, you won't have that.
Yeah, so it could be.
Of course. Getting the anisotropy is very hard because it's basically a scattered phase, and so you.
I'm talking about the discontinuity, that there have been, that the discontinuity sometimes can appear as a discontinuity in 1D, but it could be due to some phases arising.
Yeah, that was argued originally by Adam and Trump, is in fact that 3D focusing, defocusing through their tomographic models could give intermittent triplication-like features. That's really not true when you actually model their models, but if you enhance the heterogeneity by factors of 3, it does become true. So when you get up to very strong lateral gradients, then you can get the effects there. And if we accept that the tomography has kind of underestimated the heterogeneity, it's been damped and smooth, then that argument holds when you kind of correct for that and strengthen the heterogeneity. Sana?
So you showed that that in the d double prime you see a negative velocity gradient and attributed this to the thermal boundary layer. But I think that's actually treating it as a 1D Earth, because I think Ved shows in his clustering analysis that is only true for the slow velocity regions, and seismic tomography suggests it's not true in the fast velocity regions. And you
I'm sorry,
see
what
reasonably
is not
fast
true now?
velocity. Having a negative velocity gradient just above the core mantle boundary.
The strongest evidence for it is actually in cold regions. So there's detailed waveform modeling by Ding and Helmberg. It's really convincing to me. At first I didn't incorporate such strong gradients, but their models actually do very well. And they have very strong negative gradients where you have d double prime discontinuities, which tend to be the cold regions. So I would think that needs further testing in different areas, but with detailed waveform modeling, they've been able to do that better than the old diffraction results. In the fast velocity area, we have a negative gradient, but it's an assumption. It was built into the model, so beware, right? Yeah. So it could be that the gradients are flatter. The one thing I didn't mention, I'll conclude with, is we do know that the core mantle boundary is an isotherm. Okay? That's an important factoid. And even if it's got undulations, got all these lateral variations above it, that temperature has to be pretty constant because of the very vigorous core convection. So maybe within a millikelvin or something. That's a useful additional bit of information, but it's not an absolute temperature estimate. Okay, thanks. I got to get off.
Very insightful talk, reviewing seismology on the stage.